Hello, today we're going to build some rockets, and we're going to build them out of matchsticks and also aluminum foil. We'll need a few other items along the way, but those are the primary items that we're actually going to need. Now, I have to say, if you're going to do this, wear some safety goggles or wear some at least sunglasses. And if you're younger, definitely get somebody older to help you because you do have hot things flying through the air. And so I wouldn't say they're really, really dangerous, but you have to be careful because they can get hot when they fly along. So get somebody to help you and wear your safety glasses. All right, now what are we going to do today? These rockets, I want to show you what some of them look like before we really get started. The completed product, you can see they're not super special looking. They don't even really look like rockets here. But this is what they are. And there's a lot of science that we can get from looking at things like this and building little simple things like this. So this is aluminum foil coiled up with a fuel up in the top here, which you can't see. I'll show you how to build it, but there's a match head in the top. So the match head is going to be the fuel, and when we light it, we're going to have the exhaust coming out of the rocket through the back, and that's going to propel the rocket forward. So these things can go, even if you build them really rapidly and they don't work too well, they can still go 5 or 6 feet, no problem. And if you really are careful to crimp it, and I'll show you how to build it properly, they can go 20, 30 feet actually. It also depends on the type of match head you have. Some of them just work a little bit better than others. So it's a little bit up to chance, but they can go quite far away. Now you have a little mobile launcher station with a box like this. We're gonna launch it off of here. I'm gonna show you how to put the launcher rod in here. And you can carry these things around, take them in the backyard or go to a parking lot with some concrete and there's no danger of anything and launch these things. You can make them very, very quickly and launch them and have fun with them. All right, let's go launch some rockets. So here we have our rocket launch pad here. And so I open the box, I put it in. Again, you want to go vertical, you can adjust it for that. I'm going to shoot it close to a 45-degree angle. I just think it works a little bit better. So I'm going to set it up like this. So what you want to do is put it on there, and you want to just gently tap it there. And right around the place where the match head is, you can feel the match head. You could just do a little squeeze right around there to like channel the exhaust. Sometimes I find that that makes it fly a little bit better, and just make sure it can freely move up and down and that you're feeling that stop there. You definitely don't want to have your hand really close to it because, you know, it could leak exhaust gases out and it could burn you. So you want to use something with a long stick. So let's hold it up right under the match head and see what happens. We'll just hold it right there, and then that rocket will hopefully ignite and we will see what happened, the match head there. So we'll just give it a little bit of energy there. All right, that was really cool. Check it out. That was really neat. That one flew really far. It shot all the way over to the door, which is about 6 feet away, and it was very high in the air as well. Now, let me caution you. After you launch one of these things, do not go over there and pick it up with your bare hands. They are hot, like burn you hot. And I actually burned myself several times just by picking them up. Say, ooh, neat, pick it up. Well, just be careful. All right. After a minute or two, aluminum conducts heat very, very efficiently, so it'll be cool to the touch. Give it a couple minutes. All right, so let's launch this one and see how far this one goes. There's the match head right there. And that one went a little bit farther. Whoa, that one went really, really far. Let's try a more vertical launch just to see what would happen. I mean, if we're really lucky, maybe we can get it to go straight into the camera up there. Probably not, but you know, we can do some fun stuff. So we'll try it. There it goes, straight up to the camera. So we'll see what that looks like when I get the footage out. That looks pretty cool. Nice and easy, free to move. That's what you want to check. Aim kind of towards the camera. We'll just try that. So there's my flame. Whoa, it went straight into the lens. That should look pretty cool. All right, blow the fire out. Again, wear your safety goggles. If you forget, it's probably not the end of the world. If you're careful, you know, keep pointed away from yourself, but it's always better to have safety goggles on, have somebody to help you here. All right, now what I want to do is I want to look at these in slow motion. I want to see exactly how the exhaust happens. What can we learn about this thing as these match rockets fly away? And then I want to talk about Newton's laws and action, reaction forces, and why rockets work in the first place. Believe me, no matter what your level of science is, I think everyone can get something out of a discussion like this. So when we put the flame under the match head, it takes several seconds to reach kindling temperature, and then you could notice little wispies of smoke. The exhaust builds very fast. In a fraction of a second, the rocket goes the other way, and then you can actually see flames in the exhaust from this very simple rocket. And we got a bonus here as shrapnel from the inside comes out on fire and goes and lands on the launch pad, dancing across. That's why I say that these can be a little dangerous and you should be careful. This attempt was really cool. As the rocket builds in temperature and the ignition begins to happen, it launches as usual. But watch carefully as this thing lifts off of the launch pad, you can see a spiraling bundle of flame, which is actually part of the match head tumbling out of the back. When you slow everything down and see how the flame and the shrapnel tumbles, it looks, in my opinion, absolutely incredible. In fact, even the smoke looks cool. That was actually so cool that I wanted to zoom in a little bit more and get up close and personal. Look how the tumbling match head is throwing off fragments that are on fire as it arcs across the table. Let's take a look at a slow motion shot of the fuel itself, the match head burning. Take a look at the lower left-hand corner and it really looks like rocket exhaust. And the actual match head itself seems to explode from the inside out. Also, pay attention to the glistening surface that sort of moves around. I think that's actually water being driven out of the wood and the cellulose there and being driven out onto the surface. And it really dances around and bubbles the entire time. This type of shot is why I bought the high-speed camera and why I wanted to shoot match heads anyway. I'd love for you to let me know what you really think. Let's push in a little bit and zoom in before ignition. Take a look at the water kind of glistening and dancing and bubbling. And then the ignition happens, and once it happens, boy, does it go. It really explodes from the inside out. And if you look closely, you can see sort of debris and shrapnel from the match head itself just literally flying out, almost like a deep space launch of a rocket engine. I also think it's fascinating to look at the boundary between the burned and the unburned part of the match head. It's almost like an advancing flame front in like a forest fire or a wildfire. And after the burning is over, because everything is so hot, the water that was beginning to come out really comes alive and bubbles and dances. I got really lucky on this shot. Take a look at where the flame is touching the aluminum. You can see a puff of exhaust and sort of like the force swivels the entire structure to the left, and then when we launch off at an angle. This is kind of like an attitude thruster for a rocket that's operating on a spacecraft in space, right? It burned a little hole in the aluminum foil, forming a little nozzle, and we get a sideways force. Again, due to Newton's third law, every action has an equal and opposite reaction, and that sideways force turns the entire structure, and then finally we get enough force out of the back to launch it off in the new direction. Here's what happens when you don't wrap it tight enough. You get a lot of exhaust, a lot of smoke, but without it being wrapped tight, you don't actually have enough force for the rocket to lift off. So when you're building these things, you want to wrap the aluminum foil tight enough to confine the exhaust and make a nice plume for a lot of really good force. But you don't want to wrap it too tight, because if it's too tight, then it can't slip off of the bamboo skewer, and you really want to have a minimal amount of frictional force there so we can slide off freely. So there's a delicate balance there. There's a couple of things I really wanted to get across in the next shot. First, when this one launches, it goes straight and true in a perfectly straight direction, and you can actually see fire in the exhaust. Right about now, you can see the fire. And when I reset the shot again, I'm going to zoom into the fire because I want you to see that these little bitty rockets actually have exhaust in the form of smoke and also actually fire. So they really are behaving like an actual rocket engine. And then finally, what I'd like to redo is reset the shot again so that when you look at it, it's a tracking shot of the exhaust. We're going to look at the exhaust, and I want you to look at the velocity of the exhaust as the rocket is moving in one direction, how fast the rocket exhaust is coming out the rear end. In the next couple of shots, I want you to focus on the exhaust velocity. You know, exhaust velocity is one of the metrics that govern force and also efficiency in rockets. So notice how fast the exhaust is moving out. The speed of the exhaust governs basically how much reaction force you're going to get. And you can also see that as part of that exhaust, you see fire in this one. Now, in the next shot, I changed the exposure so we could see the fire a little bit better. You see the exhaust building velocity right here. We get liftoff, and then right about here, we start to see the fire come in with the exhaust particles being very hot and glowing embers there. And then, of course, it slows down as the rocket speeds away. And we got a bonus here as the match head flies out of the back and tumbles like a little meteor in the background. A little bit out of focus, but still pretty cool to look at. Here's my macro lens showing how fast the exhaust velocity is moving. For real chemical rockets, it can be thousands of meters per second. And now that we've looked at the slow motion clips, I'd like to show you how to actually build these things step by step and give you tips and pointers so that they work every single time. All right, I told you would need a few more items. The other item that you really need is a bamboo skewer. So these are the things that you would buy to barbecue something on the grill or whatever. These are just made of bamboo. They're very, very smooth there. And so the first thing you're going to do is take some scissors and grab this bamboo skewer. Notice it's a very sharp tip there. You want to kind of cut that off. You don't need it to be that sharp. Just kind of cut the end of it off so it's a little bit rounded. And then cut the bamboo skewer maybe 4 or 5 inches, something like that, 10 centimeters, something like that. Just cut it. Of course, it flew across the table there. So that's my launching rod here. And basically what you're going to do, you can see I have one in here that I've used already, doing a lot of testing already. And this one's kind of like charcoal and burned off there because I've used it a lot of times. But this is what it looks like here when you just build one there. What you're going to do is you're going to take the box and you're going to put the launcher rod into the box. Let me move these off to the side. And something like this. So you have like a mobile launching platform like this. So notice the box, close the box, you open it up a little bit, or you can open it the other way like this, however you want to do it. And you can adjust the angle by adjusting how this thing is closed. Maybe it works a little bit better like this. So if you push it up against the box there, you can adjust the height of this thing by adjusting where the base of the box is. I usually like to launch it somewhere around 45 degrees. If you want to go vertical, you can launch it more something like that. And that would look really cool too. Right? All right, so there's your launching platform. All right, so let's make these things. There's a little bit of trial and error to it. They're not a perfect science, but this is basically what you're going to do. So you take the match head. So this is the match head here. Grab some scissors and just be careful and just kind of like work it and cut the match head off. Of course, they can often fly across the table. You get the idea here. And what you can do, if you want, is you can make a bunch of these at once. So you can make like 10 of them at once. I mean, I think I made 5 of them. The other day. That one's split in half, so we're not going to use that one. And once you get good at it, it might take you 1 or 2 minutes per rocket to make these things. So I'm going to put 3 of them together. What I'm going to do is I'm going to pull some foil out and rip off a piece of foil like this. Notice I did not measure anything. So this isn't. I shouldn't say this is not rocket science because it is rocket science. But what I'm trying to say is, if you follow my general guidelines, you will get a rocket that works. And then you can play with it yourself there. So you basically are just going to cut a strip of aluminum foil. What are the dimensions of this? Notice I'm not measuring anything. It's maybe 2 or 3 inches in width there. And it's just the length of it there. Now what are you going to do is you're going to go up a few inches from the bottom there and then go at an angle. And I'll explain why you're doing this in a second. You want to go at an angle and make a little, kind of like a little house is what I call it. A little polygon like that. That's what you're looking for. What are the exact dimensions? I've seen some videos out there where they give you a template and all that stuff. I find that it doesn't really matter. I mean, now why are we making it this shape? I'll show you, tell you a little bit more about it as we get done. But basically, it helps the flight path. Making it this shape basically gets the center of mass, the center of balance on the rocket in a good place so it can launch stably. If you just make it a straight rectangle, it'll still launch. It'll just a lot of times tumble because it's got too much weight in the tip. So up here is going to be the tip here, and this is going to be the back end, and it just generally works out better. Have I done an exhaustive scientific analysis of this? No, I haven't, but I've done a few tests, and this seems to be the best shape. So notice some of these are bigger, some of these are smaller. I'm not really measuring any of these things. So they're a few inches on each side. All right, now what are we going to do? The number one thing is, do not try to make the rocket out of the matchstick wood itself. Notice this is rectangular and it doesn't slip in and out of the rocket like nicely. What you need is a cylinder, which is what this bamboo stick is. It's nice and smooth, okay? So what you're gonna do is you're going to take your aluminum foil like this. You're gonna put your matchstick in, and then you're going to put the launcher like this, so that the tip of the launcher where you cut off the launcher is like this. Now I've tried it both ways, where the match head was facing down, and then I've done it where the match head's facing up. And to be honest with you, I can't notice a huge difference. I think it may work a little bit better when the match head is down, because the exhaust is, this is going to be the exhaust end of the rocket here, and then we're going to pinch this end up here. So I think it works a little better like that, but you know, it's hard to say for sure, because there's a lot of other things going on. So what you want to do is you want to put them together like this, and you want to roll this thing up. But the trick is, and you have to do this, you have to roll it pretty tight. And it's hard to do because aluminum foil crinkles like this. So what I figured out is that if you roll it a little bit and get another bamboo skewer and just kind of like draw a little line here, kind of to tuck it in, to help it get tucked in. Notice this thing popped out. And then lift it up, and then continue rolling it as you lift up. Once you get it started, notice I got it started, then I can kind of pull on it. I can kind of like pull and give some tension as I roll it up like this. If you try to do it all on the surface of the table and just roll it like Play-Doh or something, you can do it sometimes, but it often doesn't work. So now it's wrapped up, okay? Now what do? You have the fuel up here at the top, and you have the match or the launcher at the bottom. Then you grab your finger and you just pinch it, and I can feel the match head. The match head itself is about right there. And that's about as much space as you want at the top. If you have less space, what's going to happen is these matches get really hot when they burn. And so if you don't give enough space up there and enough mass to contain it, then it's going to burn a hole through. I have many of these rockets where the exhaust just kind of like made a hole in the aluminum because it got so hot, and it just found a weak spot, and it shoots right through and melts a little hole through. So you need enough mass up there to pinch it. So pinch it with your fingers. That's obviously not going to be good enough. And then what you can do is bend it over. What I like to do is bend it over once like this, and then crimp it with some pliers. So crimp it like this, just like this, okay? And then after that, you can either use the pliers or your fingers, whatever you find easier. Do it one more time, like this, okay? And then you can leave it like this, to be honest. You can just launch it like this. But I just find that going, notice I bend the corner up here, and then I bend the corner on the other side over here, and then just kind of get your pliers, and see, it doesn't always work, but you get the idea. You get your pliers to fold it down, okay? Fold it down. And it doesn't look beautiful, but it gets the point across. And once you kind of get it bent, then you can really give some force on those pliers. Make sure to try not to crush the match head that's in there. Okay, so notice it's not like super pretty. It's not like folded like nicely like a rocket, but you can see some of the other examples where I was able to do a little better job. I think this foil I have here is heavy-duty aluminum foil, which is a little thicker. It's a little easier to, or a little harder to bend, whereas when I was doing these other ones, it was regular aluminum foil. So it's a little easier there. All right, now what you want, and you can kind of go and twist around to kind of make it nice and tight. Just kind of continue twisting it like this. There. Let me show you the number one thing to have good results here. You need this stick here, this launcher, to be able to slide in and out very, very easily. It's very, very easy. There's no friction. I'm not pulling on it and yanking. I don't feel any jerkiness or anything. And if you try to use this matchstick here, because of the corners, it doesn't move so smoothly. You need to have very, very smooth motion. So this one is done. Now notice there are no fins on this rocket. The fins that you see there for this is not really necessary. You're going to see that they fly straight and true. But if they were to continue thrusting throughout the sky like a real rocket, thrusting for 7 or 8 minutes, then you have to have some stabilization fins of some kind to keep steering it. Or you need the engine itself to be able to swivel. That's called gimbaling in engines for rocket launches. But this doesn't have any gimbal because the thrust just comes out one direction and there's no way to steer it. But that's not the point of this. You know, we're just trying to learn why it launches in the first place and how it works. All right, I hope you agree that the slow motion footage of these little match rockets are really cool to look at and actually gives us the framework to talk about how rockets work anyway. We've all seen rockets launch. Lots of fire comes out the back, rocket goes up, right? But you know, there are other kinds of rockets. Rockets work in the atmosphere on Earth, but rockets also work in space. When you light a rocket engine to go to the moon, there's very little oxygen up in the upper atmosphere, way above where the spacecraft is orbiting. And there's a little bit of atoms, but there's almost nothing up there. So obviously rockets can work in vacuum, right? They work on other spacecraft to reorient the attitude thrusters to point the spacecraft in different directions. But there are other kinds of rockets. Those are called chemical rockets with a chemical reaction. But there's also rockets that work on plasma propulsion, which is more of an electricity powering the rocket, or even nuclear power powering the rocket. So we're going to touch on all of them today. But they all have one fundamental thing in common. What you're doing with a rocket is exhaust is flowing out the back of the rocket at a high speed, and somehow through the magic of physics it pushes the object the other way. Now the biggest misconception is that people think that the rocket is pushing off the air. It's like a ladder. People think the atmosphere is like a ladder, and when you're exhausting in the atmosphere, it's pushing off the air, and it's like you're climbing the ladder into orbit. But that's not the case at all. They obviously work in vacuum. So to understand how they work, we have to talk about Newton's laws. You probably heard of this guy, Isaac Newton, 3 famous laws of motion. We're not going to go into this crazy level of detail for any one of them. We're going to talk briefly about the first one, and the second one, the third one, governs rockets, right? So the first law of motion of Sir Isaac Newton is basically the law of inertia. You may have heard that an object in rest tends to stay at rest, but an object in motion tends to stay in motion in a straight line unless it's acted upon by some outside force. That's what we call inertia. What it means is if I have this marker sitting on this paper, it's at rest. And it will stay at rest forever unless some force moves it, like I could jiggle the paper, right? Also, if I go to space and I throw this thing, then it will travel in a straight line forever, right? Without any other forces. And it will go in a straight line unless some force pushes it. Like it could be gravity, it could be a rocket, it could be anything. So objects are either at rest or they're in motion in a straight line. That's what the first law of motion says. The second law of motion is summed up by an equation, F equals ma. And basically, the force on an object is equal to the mass of the object times the acceleration. So it ties together pushing on an object with how much the object accelerates. A rocket, as you might guess, is pushing on the back of the ship with some kind of force, and so the force is in this equation, and then the ship has some mass, that's in this equation, and the result of the force means it accelerates, it changes its velocity. That's the acceleration here. So Newton's second law of motion ties together the pushing force with how the motion happens, the acceleration. That's what the second law of motion is. The third law of motion, I know that you've all heard, and it basically says every action has an equal and opposite reaction. Now, it's not a great wording of the law. I can put it into my own words, and you can read whole books about it, because it doesn't use the word force in that sentence there. What it basically is saying is that all forces, when you have two bodies together, could be my hand and the board, could be my rear end sitting on the chair, that's two bodies coming into contact. A rocket and the exhaust flowing out the back is also two bodies because all the atoms coming out are separate from the rocket, two different bodies that are technically touching right at the rocket nozzle in the back right there, right? But it could be any two objects. Anytime you're pushing with any force is going to involve two objects by definition, right? Or two items of some kind, right? For every action force, there's an equal and opposite mirror image, you can think of it, reaction force happening at the same time, right? Let me give you a couple of examples. But as I give you the examples, I want you to think, basically, that forces come in pairs. When you have two bodies that are interacting with forces, there's an action force and there's a reaction force. They always come in pairs. But as we go through the discussion here, I want you to remember something that is often lost even in physics lectures or whatever. It's lost, but it's critically important. The action force and the reaction force act on the opposite body. They never act on the same body. The action force, I'll say it one more time, it's pushing on one of the bodies. But the reaction, the other force, is not pushing on that same body, it's pushing on the other body. Because remember, it's always related to two things here. Let me give you a couple of examples. Here is my hand, it's a body. Here is the board, it's a body. That's two bodies here. If I push on this, then there is an action force and a reaction force. And when I push on it, my hand is pushing on the board. That is an action force. That force is acting on the board. I'm pushing on the board, right? But the board is pushing back on my hand. But notice that that force is not acting on the board, it's acting on my hand, the opposite body. So hand acting on board, board acting on hand. The action and the reaction force always act on each of the two bodies in the problem. They never act on the same item. Like it's not like one force on the hand and then another force on the hand. That would be two forces on the hand. That isn't the way action and reaction works. And it's the same thing with rocket exhaust. I'm going to get to in a minute, but I'll just tell you the punchline. The exhaust is being, the chemical reaction is pushing the exhaust out the back. That's a force on the exhaust. The reaction force is the exhaust pushing on the rocket. And that's what sends the rocket this way. So it's like they're both going separate directions. The exhaust is going this way and the rocket's going this way. The one force is acting on the exhaust atoms and the reaction force is acting from the exhaust atoms pushing back on the rocket, acting on the opposite bodies. That is the number one thing you get in trouble with these kind of physics problems. When you take physics, you start thinking that they are acting on the same thing, but the action-reaction pairs always act on the opposite body. All right, let's think about sitting in a chair. If I sit in a chair, gravity's obviously pulling me down. My rear end is pushing on the chair. A force is acting on the chair. There's a two-body problem there, the chair and my rear end, okay? My butt is pushing on the chair. The reaction force is the chair pushing up on my butt, and you can feel that force. That's the force. If you put a nail in that chair, you absolutely will feel that force, okay? So, butt acting on chair, chair acting on butt, okay? Opposite bodies in the two-body problem that you have there. Now, what I want to do is draw a picture of rocket exhaust, right? But before I draw the picture, I think I can just make a mental image for you. Imagine that we are standing in a boat. The boat is floating in the water, okay? And of course, there's all kinds of forces. There's wind, there's all kinds of things happening, but I'm on a very still lake. There's no wind that day, and I mean no wind. No birds flying. I can't feel the breeze at all. There's no current in the lake. You might even think of it being on an ice sheet or something like that with no friction at all. But anyway, let's think of a lake. I'm standing up in this boat, perfectly balanced. I'm not shaking, I'm not moving, I'm not jiggling. I am absolutely still. There is not a single wave or ripple in the water at all. But I'm holding in my hand a bag of rocks, all right? If I take a rock and I throw it out of the back of the boat, what do you think will happen? And forget about little rocks. Think of a bowling ball, a big, giant, heavy ball. I'm lifting it up, very heavy, and I turn sideways and I throw it. What's going to happen? As I throw it, I'm acting a force on that ball, and the reaction force is the ball is going to push on my hand. You can feel it in the inertia. It's heavy. You can feel it resisting. You can feel the push on the ball and the ball resisting you and pushing back. And as soon as the ball detaches your hand, you're going to see the boat move this way. The ball will go this way. The boat will go the opposite way. Now let's say that instead of a single ball, you had like 50 balls. And you had like a machine just feeding you the balls. So I grab a ball, throw it. I grab a ball, throw it. I grab a ball, throw it. And so it might be a herky-jerky motion, might be like, whoa, but that boat is going to start moving this way. That is rocket exhaust. Notice that the bowling ball is not pushing off of air. It's not reacting with the air in the atmosphere. If you had a similar situation in space with an astronaut, and not be on a lake, and an astronaut was floating, with a backpack full of balls and started throwing them, then the same thing would happen. The astronaut would be moving the other way. There's no air involved. I'm talking about in a spacesuit outside the ship, the astronaut would be propelled. The only difference is that in an exhaust situation with rockets, the balls are atoms or molecules. So each individual atom of exhaust, like when you burn this match, there's a lot of carbon dioxide, CO2, and H2O, water. Each of those molecules has some tiny mass. Tiny, tiny, but there's trillions of them. We as humans cannot fathom what trillions of anything is. But it's an unimaginably large number of these tiny little balls. And they're not balls, they're molecules, but you get my point, okay? Each one flying out the bag is imparting a reaction force to the rocket. But when trillions of them are happening, then you don't get the herky-jerky motion. You get a smooth launch, which is what we see. We don't see it as a jerk, 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 jerk because there's so many of them that the motion is smoothed out like that, right? And that is basically what a chemical rocket is doing. So let's draw one little picture just to say that I drew a picture for you, right? Let's say that here's my spaceship, right, like this. And at the business end in the back is some kind of rocket nozzle. That's the exhaust coming out of the back, right? Let's say there's some person here, Mr. Astronaut or Mrs. Astronaut standing there, and there's an infinite supply of rocks or something. And what they do is they take and they throw one of these rocks out the back end. Now, this rocket is a weird, complex shape, but you can still imagine it being maybe a flat plate that it's up against, and it's kind of like pushing off of a flat plate or something like that. Or maybe they're emerging from a flat plate, or maybe his hand is going over there and pushing them at this position or whatever. But anyway, once the first one flies out, he grabs another one, and then it pushes that one, and another one, and another one. And if you draw a very large picture of this, like if you put the end of the rocket here, and the rock or the exhaust particle right there, then what would basically happen is there would be some force right here, which would be the action force. And that would be the rocket pushing on the exhaust particle. But then there would be some reaction force. And notice it wouldn't be acting on the same object. It would be going the other way, same length. I did a bad job. This arrow should be the same exact length. But this would be the reaction force. But the main difference, and this is a blow up of what we have up here, so the whole rocket is connected over here. But notice that the action force is acting on the rock. And the reaction force is acting on the rocket. Just like the lake, just like sitting in the lake. Now, when we burn things, there's a chemical reaction that causes a lot of heat, and the heat causes everything to want to rush away from each other. And you have this nice little funnel we call a rocket exhaust nozzle at the end, which channels it all in one direction. So instead of an explosion going on all directions, it channels it to only force it in one direction. So the action force is pushing on the exhaust from the rocket to the exhaust there, because don't forget, if it's really burning here, then at some point there's an injector plate and fuel there. So at the moment of ignition, the very first particle is being pushed off the ship. At the moment of ignition, right on the ignition plate itself, the first molecule is formed right there, and it's pushing off of the ship because it starts from there. So the force is acting on the exhaust particle, and then the reaction force is there's a force acting backwards on the rocket itself. Okay? And that's always the nature of forces that involve two objects. There's always an action force and a reaction force. So that's how rockets basically work. Where does all the heat come from? That gets into chemistry. For a chemical rocket, it comes from the rearrangement of the electrons that are going from the fuel and the oxidizer. In the match, there's phosphorus in there. There's lots of things. There's sulfur in there. And then it's combining with the oxygen to make a very hot exhaust gas. Other rockets use hydrogen and oxygen, or maybe kerosene and oxygen. You've heard of kerosene, right? Methane, CH4, there's a lot of hydrogens in there, and oxygen, but it's always going to burn with oxygen. At least that's the way we build chemical rockets today. I shouldn't say always. There are rockets that don't use oxygen at all, but they're used in space when there's when you don't want to carry oxygen like that. There are other oxidizers other than oxygen, but for ground launches, it's almost always oxygen of some kind. Okay? And you always want to make a high-speed exhaust. Now, chemistry, like chemical rockets, hydrogen plus oxygen, obviously explosive, methane, things like this with the matchstick rocket, they can make high exhaust. But what if you wanted to make even higher exhaust, higher velocity exhaust? Then you could get your rocket to go even faster, right? If you think about a chemical rocket, let's take the simplest reaction I can think of. You have hydrogen, which is a gas, or actually it's a liquid whenever you put it in the liquid oxygen, so you can do it as a liquid, plus oxygen, do it as a liquid. This is what the space shuttle used for its first stage. And that's going to yield water, H2O, and it's going to be a gas, all right? Now, you may remember from chemistry, we have to balance this because we have to have the same number of atoms. So basically, we have two hydrogens on both sides. That's correct, but we have two oxygens here and only one here. So we have to put a 2 here, but now we have 4. 2 times 2 is 4 hydrogens, so we have to put a 2 here. So this is the balanced chemical reaction. And it basically says 2 parts of hydrogen, 2 moles of hydrogen, and 1 part of oxygen, which in chemistry we call a mole, yields 2 parts. It's the ratio of how much you need of everything to make a balanced reaction, because you have to have the same number of atoms on both sides. But what I'm leaving out of this equation is all of the heat. You see, this is telling you the big picture, but what's really happening is the electrons are moving around and rebonding and making this product. And they're in a much lower energy state. So when the electrons come crashing in, forming this molecule, and they go to a lower energy state, there is a ton of heat coming from the crashing in of these electrons into lower energy states, almost like a meteor coming in the atmosphere and it gets hot, right? And so this is not a liquid, it is a gas and it is channeled out of the back. But no matter how hard you try, you're only going to get the exhaust of this water to come out at a certain speed because it's all governed by how much energy is released in the chemistry. So chemical rockets have a fundamental limit. You can't make them with more thrust or more efficiency than a certain point because it's governed by chemistry. And the chemistry is only going to allow the exhaust velocity to go up to a certain point, right? How do you get around that? I'm not going to draw any pictures, but I'll tell you that there's something called a plasma rocket. Right? A plasma rocket may not use a reaction like this. It may use a xenon gas, or sometimes it's argon gas. These are noble gases, and the reason we use them is because they are heavy. They're heavy atoms on the right-hand side of the periodic table. And so what you can do is if you can ionize these things and make them charged, then you can use electricity because, you know, you can use like charges repel, you can use antennas, you can do there's lots of techniques to accelerate plasma, right? And confine plasma and channel it. But what you're able to do is, whereas this exhaust velocity is governed by the chemistry and the chemical bonds, this thing is only governed by how big of a power source you have. So if you have xenon with solar panels, you can get the exhaust going pretty darn fast. But if you had a xenon thruster with a nuclear reactor generating megawatts of energy, then you can accelerate this argon, ionized argon, out of the back much, much faster than water. And remember, the whole thing works by throwing things out of the back. And so the faster you throw them out of the back, the more force essentially that's happening there, and then you get a more incremental force off every single molecule that you throw off the back or atom that you throw off the back. So you're limited by chemistry. But with plasma thrusters, and there's many kinds of plasma thrusters, and I worked on a couple of myself, you can accelerate the plasma out of the back much, much higher. And because you can get the velocity going much, much higher, then you don't need to carry as much fuel, right? Because remember, you have two things to play with. You have the mass of each individual particle and you have the exhaust velocity. If you could crank up the exhaust velocity really fast, then you don't need as many particles. You don't need as much fuel. And if you don't need as much fuel, then your whole spacecraft can be smaller. And if your whole spacecraft is smaller, then it accelerates faster because remember, F equals ma. The mass influences how the spacecraft accelerates. So if you can get the exhaust velocity high, then you can accelerate faster with less fuel. And you maybe can go to other star systems and things because using this kind of reaction, you're never going to get anywhere. You accelerate for 5 minutes and you're out of fuel because it has to burn really fast. And get it all done. Chemical reactions is, it's not really, you can throttle it by allowing more or less fuel in, but that's all you can do. You can't change the reaction. You can't change how much energy per unit is coming out like this. But with this thing, you can turn your reactor up and down, generating 4, 5, 6 megawatts down to 3 megawatts, and you can throttle the exhaust velocity. So deep space plasma propulsion, big, big deal. And then there's fission reactions and fusion reactors and all kinds of ideas. And it's dangerous because this is nuclear reactors and you can have meltdowns and things like that. But that is how we go farther. We're not going to go farther in the solar system. I mean, we could get to Mars, maybe even Jupiter with human missions with chemical rockets, but to go way far out in the solar system and certainly to go to another star, it's not going to be with chemistry. It's got to be with something else, a nuclear reactor, or even there are crazy ideas for giant sails which allow sunlight to push like a sail, literally a sailboat in space, where the sunlight is pushing you, or a laser beam can push you, something like that. All of that to say that I wanted to show in this lesson a cool little thing you can build at home. You can build a matchstick rocket, and I could have cut it right there, and I could have said, build it, it's neat. But I wanted to go a little deeper. I wanted to show you, why does it work? And would this matchstick rocket work in space? Well, that depends on the match head. Does this match head have oxidizer inside of it, or does it need any oxygen from the air? So it depends on what you have there. But in principle, if you have a chemical reaction self-contained, right, then you don't need any air for the exhaust to push off of. I wanted to drill that home, and I wanted to show examples of that. I like taking simple things that look just like neat and really diving in. Right? And then taking it a step further to, let's not talk about chemical reactions, let's talk about plasma reaction or plasma thrusters or nuclear reactions, things like that. And even though we just touched on it, you can see that even simple things can lead to really cool discussions. So I really like your feedback. Did you like what I did? Was it neat? Did you like the slow motion part? Did you like the discussion part? Or should I just cut that out? Like, that's fine too. I can do that. Please let me know what you think, and I will see you in the next one.
Learn anything at mathandscience.com.